Hello, everybody, and thank you for joining us for this session of Vertica Unify 2021. Our next breakout session is entitled A Deep Dive of Complex Data Types. I'm Paige Roberts, Open Source Relations Manager at Vertica. I'll be your host for this webinar. Joining me are Vertica Technical Leads Deepak Majeti and Ryan Rolke. But before we begin, I encourage you to submit questions during the virtual session. You don't have to wait to the end. Just enter your question into the Q&A box as it occurs to you. It's on the right-hand side of the screen. There will be a Q&A session at the end of the presentation, and we'll answer as many questions as possible during that time. Any questions that we don't address, we'll do our best to answer offline. Alternatively, you can visit the Virtual Developer Lounge to ask additional questions and continue the conversation with our engineers and product experts. And yes, before you ask, this virtual session is being recorded and it will be available to view on demand this week. We'll send you a notification as soon as it's ready. Be sure to stick around to the very end of the presentation for the code that you'll use to participate and gain points in our Analyze to Win competition. Now, let's get started. Over to you, Deepak.
Thank you, Paige, for the introduction. So this is going to be the overview of our talk today. First, I'll give an introduction to complex data types. Then I'll quickly cover the support we have in Vertica for complex data types. And then we'll talk about some of the optimizations that we implemented to get good performance with complex data types. And then we'll move on to some performance evaluation, and stay tuned for this section because we found some pretty interesting results using complex data types comparing with traditional techniques. And then we'll talk about some best practices when and how to use complex data types. And then we'll give you what is coming in the 11.0 release. And we'll talk about some of the feature work that we're doing in the roadmap ahead. All right, so what are complex data types? I'll directly explain them with some examples on the slide here. So on this slide, we have three commonly used or popularly used complex data types. The first is a row complex data type. In this slide, we have an example of a customer who has a row with two fields. A row is basically a complex data type that contains a set of fields. And in this example, we have two fields, namely first is the name with type varchar, and the second is a ID field with type integer. And on the right, we have some sample data. And row is also commonly known as struct. So in the imperative world, we call it struct. And in the SQL world, we sort of use row to refer to the same type. The second complex data type that is popular is an array. So an array is nothing but a collection of similarly typed elements. And in this slide, we have an example of ship dates that is an array of type where the element type is date. This encapsulates a collection of date elements. So on the right, we have some sample data for ship dates, and you can have any number of elements of date type. And then the third popularly used complex data type is the map type. So map is nothing but a collection of key value pairs, and that's also from the imperative world, which is commonly used in C and other programming languages. So in this slide, we have an example of HTTP requests where the map's key type is a varchar and the value type is also a varchar. And on the right, we have some sample data for the same. So here we are looking at HTTP requests. So the key could be pragma, and the value is a no cache, or and so on and so forth. So a map, since it is a collection of key value pairs, can also be handled as an array of row where the element type is key and the second field is a value. So a map is nothing but a collection. So we have an array there, and the element type is a key value. So you have a row with the first field as key and the second field as value. And in this example, we have varchar for both. So those field types will be varchar as well. So in the previous slide, we saw complex data types where the fields were all scalar or primitive types, but complex data types can be nested as well. So on this slide, we have an example of an inline nested complex data type. So we have this web sales data, and we can encapsulate all the data using this web sales complex data type. So here, just hypothetical example where we have some customer key for each sale. We have some orders placed by the customer on a particular sale. It's a page counter. So we are tracking all the pages that the customer, all the user visited, and we want to see how much time they spent and what are all the pages they visited. So there are some fields that you can use to encapsulate. So for instance, here you can use duration seconds, which is an array of integers to track each of the pages duration, the time spent. And then finally a ship date for the orders that were placed. What is the ship date chosen by the user? So what are uses of some of the complex data types? The main primary use case for complex data types is to co-locate related data in the same row and take advantage of locality. In the traditional ways to store this data, we would either have to normalize or duplicate. So on the right, we have some sample data where we have a column username and then all the set of search words used by the user. So either we can use a complex type for all the search words, or in the traditional way, we'll have to normalize search words and hit the cost of a join, or we duplicate the username and we end up taking extra storage cost. So that is one advantage of using complex data types compared to the traditional techniques. And the other use of complex data types is that they are a natural fit for data coming from domains where complex types are first-class citizens. So if you look at NoSQL, Python, and other imperative languages, they all use complex data types in their data analysis or data generators, and data coming from those sources naturally have complex data types, and supporting them in SQL will allow us to now process data coming from those domains as well. And the other use case is that maps are generally used to store sparse data. So if you have the HTTP request where the keys or the headers are not the same for all the clients, so you have sparse data coming into your storage, so you want to efficiently store them. So map is a type that you can use to store sparse data, and this is prominent in Web 2.2 applications that are common today. And as a result, once we avoid joins and use complex types, we can greatly simplify the query analysis. And we'll see that using some examples as well in the following slides. The two reasons that allow us to simplify the query analysis. One is that we avoid the joins, and also complex types come with rich functions that can iteratively process the data. And these two features allow us to simplify the query a lot. And like I said, we have some examples in the coming slides. All right, so what are some of the use cases of complex data types? As I mentioned, locality is one of the primary benefit of complex data types. And so any query that can exploit locality is a good use case for complex data types. So for instance, if you look at queries in clickstream or search applications, they all have a set of words or a set of data associated with each row. And then all those applications touch all the data. So they have a lot of locality inherent in their queries. And in those cases, we can exploit complex data types. So some of the popular queries, if you look in these domains, are basically count the number of. So in the previous slide, we saw an example where we have a user and a set of search words. So counting all the search words or finding a specific search word are all interesting use cases, and these can benefit using complex data types. And arrays and sets are primarily the complex types that are used for this application. So on this slide, we have schemas for the traditional way and the schema when you use a complex data type. So in the traditional approach, you would normalize or flatten the data or duplicate the data because it's just a few fields. So you will end up having a column with username and words varchar, but the username would repeat for each of the search word made by the user. On the other hand, you can use the set type instead and store all the search words for a given user in the set type, and you avoid duplicating the username on multiple rows. So let's look at the count and the find queries, how those look for the flattened versus the complex type use case. So in the flattened approach, you would select the username. However, to get all the count, you would have to get distinct words and also group by the username. So it's not a straightforward query. You have to have this group by operation and also a distinct operation. However, if you look at the corresponding count query for the set case, which is below, you'll just have to use a simple apply count function that will iteratively go through the words and give you the count. And the find query is similar. It is the same in pretty much in both the use cases, but you'll see that there's a performance implication because we have all the data co-located in the same row versus they being present on multiple rows. So it's a search or find in the traditional world is basically you apply a predicate words equal to Xbox, and using sets, you use a function contains that will take the set column and the search or the find argument. All right, so let's look at somewhat more complicated examples. So we looked at locality. Now let's look at how we can avoid joins as well, or basically substitute joins using complex data types. So here, this is following on the web sales complex type that we saw earlier. So if you want to represent the same data of web sales in the traditional world, you would have these three tables. So you'll have the web sales table with some keys to track the orders and the page counters. So you will have the session key, the customer key, and the ship date in the web sales table, and you'll have an orders table for each of the orders placed by that session, and then you will have a page counters table tracking the pages visited during each of the sessions. So this is the normalized way to store the data from the web sales application. However, if we use complex types, we can use the same schema that we saw earlier. So you can have the customer key, ship date as primary columns, and you can have orders, which is an array of a row type, and you can have page counters, which is a row of a page metadata and duration seconds. So you want to keep them separate because your primary applications are to look at the duration, and then based on that, you want to look at some of the page metadata. So say you're a web analyst and you want to look at your customers who are making these purchases, and you want to basically get the maximum duration spent, the ship date of all those customers who place more than 5 items in a session. So you want to know if they're taking advantage of your shipping policies or shipping offers, and you want to see why they are spending so much time on a particular page. So you're curious about this. To analyze this query or question in the traditional way, you would have to write this whole big query with all the joins. So you'll have to join the page durations with itself, and then join the result with the rest of the other tables. So you have this long query that almost fills the whole page to get the result. So not only is the query long, but also the query plan is expensive as well. So if you look at this query plan with join, you have 3 load steps. You have a join operation, which joins the page counters with itself. You have an aggregate plus group by to get the count of the orders. And then you have a filter step to filter based on the predicate of 5. And then you join all these results together. So this is a query plan with join. Now, if you move to the complex types, the query as well as the plan is much simpler. So the query, as you can see on the slide, is simply to get the max duration page. You get that by using the apply max function, and then you use that value to get the index in the array, and you use that index or the page field to get the metadata of the page that has the details of all the pages of that durations. And then you can apply a simple apply count function on the orders to get your final result. And similarly, the plan is also very straightforward. You have a scalar function, apply count, and the filter step to prune out the orders that are of interest. And then you have this expression evaluation to get the page metadata or the page that has the maximum duration. And one more interesting point is that here, the scalar and filter step can also be pushed down into the lower step. So currently we do that only for the scan step, but we are working towards that optimization where we can push these filters to the lower step as well. So it's only possible with complex types because it's a scalar and a simple filter function. However, if you look at the plan for the join case, you have a group by with a filter step, which cannot be pushed down into the lower step. So complex types allow us to implement more optimizations to the plan as well, because they allow us to use scalars and simpler functions to get the result. All right, so moving ahead, let's look at what file formats out there support complex data types. So complex data types are supported by many popular file formats. JSON, for instance, supports arrays and objects. And some of the properties of JSON are essentially it is schemaless, it's row-oriented, and it's text-based. Because it is schemaless, you have to have redundant column names or keys on every row. And Avro is the other popular file format used today. It supports records, enums, arrays as some of the complex data types. It is one step ahead of JSON. It has a schema. It is row-oriented, and it is binary compressed as well. So it doesn't have the redundancy of the column names on every row, and it can compress well because of the binary representation. And apart from row-oriented file formats, we have Parquet and Orc that are column-oriented as well that support complex data types. So they support arrays, maps, and structs or rows. And they slightly differ in the way they encode the complex metadata or the hierarchy. Parquet uses this repetition and definition levels that are derived from Dremel to represent the hierarchy. Orc has another encoding mechanism. The table here essentially summarizes the features or properties of these file formats. JSON, Avro are both row-oriented. Avro has a schema and has a binary representation, and Parquet, Orc are columnar, and they have schema as well. All right, so now let's look at what are the ways we support complex data types in Vertica. So Vertica primarily has 2 ways to support complex data types. First is the flex tables. Flex tables use a text-based format called VMAP to store the data as key value pairs. It is schemaless and weak type, very similar to JSON in that sense. And as I mentioned, data is represented in VMAP and text format. And the primary advantage of flex tables is that you get flexibility at the cost of performance. So if your data doesn't have a strong schema, say every row has different fields, then you need the flexibility to analyze the data, and flex tables give you that. Now, say your data is strongly typed, then we have a new feature that we implemented in Vertica, namely the strongly typed complex data types. So we added new types to the Vertica system. And as I mentioned, they are strongly typed. So you can aim for the best possible performance. So we implement them natively in Vertica, similar to other primitive types, and the idea is to get the best possible performance. So on the slide, we have some sample data for hypothetical restaurant locations and restaurant data, basically. And this is in JSON format. So you can see in the first row, there is some data for Bob's Pizzeria, where the name, cuisine, locations in the menu are the fields. However, in the second row, you have an additional field called capacity that is missing from the first row. So to store this data, you can use flex tables, and because they give you the flexibility, you don't need to have the same schema in every row. So flex tables can be used in this scenario. You create a flex table called restaurants, and you simply copy the JSON data using the FJSON parser into the flex table. And this is what you get when you do a select star from the restaurants table. You have an identity column that identifies each of the row uniquely, and then you have this raw column that stores all the row information. So all the fields are all clubbed into a single column, and they use this proprietary format called VMAP binary format, which is essentially a key value data type, and it is backed internally by a long var binary type. All right, so once you get your data, you analyze it, and now you know what fields are of interest to you, you can turn your schemaless data into strongly typed tables. So once you know what fields are of interest, say you are only interested in the name, cuisine, locations, and menu, you can alter the table restaurant to add all these columns, and you can delete the raw column if you don't need it anymore. And you can copy the data again to the restaurant's table, and you will have all the fields in optimal format, the binary format, basically, and you will get the best possible performance after you materialize it into their native types. As I mentioned, the other approach is to use strongly typed tables in Vertica if you want performance, and if you know your data has a strongly typed schema. We added 3 new types: the row, array, and set. Set is similar to an array, but it is optimized for a lookup use case, so not allow for duplicate entries. So if you know the order is not important and there are no duplicate entries, then you can use a set to efficiently get some lookup queries or even count. So set is more optimized than array if you know the order is not important. And on the slide, we have an example of complex data type in Vertica. So you can create an external table from Parquet, say orders, where the first column is a simple row, and the second column items is a nested array, and the third is a combination of array and row types. And we support the dot notation and the array index notation as well, that is popular in the imperative world. So you can use customer.id to get the ID field from the customer column, and you can use the index notation, items of 0 and 1, to get the inner element of the items array, and you can do a combination of both as well. You can say contact of 0.mobile from orders. All right, so what are some features unique to Vertica? So we implement the set type that is sort of unique to Vertica. BigQuery has something similar, which is what they claim to be array, but they don't have the traditional array implementation, and they have some limitations there as well. However, Snowflake and Spark do not have a set type. And Vertica also has full support for null and empty arrays. So we have the full semantics that SQL specifies. However, BigQuery and Snowflake have, and Spark have some limitations in this space as well. And finally, we have bounded arrays that help the resource manager to execute efficiently. So if you know your arrays have an upper bound on the number of elements, you can specify the bound, and resource manager will know how to generate the plan efficiently because the bounds are known. I think I have an example of that on the slide. So you can see that the inner array has a bound of 100. So we know that it cannot be more than 100 elements. All right, so with that, I will hand it over to Ryan to go through the rest of the presentation.
Thank you, Deepak. Let's take a look at a couple of details as to how Vertica represents complex types inside the query engine. So when you query a complex type column, the result that you're going to get on the client side is a JSON formatted string. But we represent the complex type data inside the query engine very differently. In particular, we represent the complex type values using a binary format, which is organized in a columnar representation. This representation aligns with the way that Vertica's execution engine has traditionally worked, which means that complex type queries can exploit all the same benefits that queries against non-complex type data can. Complex type values are represented using a combination of structure data and value data. If you have a row type, for example, then you'll have a structure column indicating whether or not each row is a null value. because a null row is a distinct value from a row with all null fields. In addition to that, there would be one value column for each field of the row value. So in this example, we have a row with two fields, ID and name. We have two columns for the ID and name respectively, and we have the structure is null column on top of that. If you have an array complex type, then we have more structure data columns. We have two structure columns for each array dimension, a column to indicate whether each array element is null, and another column to indicate the offsets of each array element. These offsets are used to index into the final column, which is the array values column. This values or elements column contains all of the array values packed together. This organ representation means that when you query a complex type and you do a field selection, we don't have to materialize the entire complex type. We only have to materialize the required fields. If you run a query such as select customer.id from requests, then we don't need to materialize the structure column or the name column from the data source. We only need to materialize the ID column. Similarly, if you run select count customer from requests, then we don't care about what the values of each field are. We only care about whether or not this complex type is null. Therefore, we only need to materialize this is null structure column. Having seen those details, let's see how the performance of complex type queries measures up with our expectations. First, let's take a look at flattened data versus complex type data. We built a micro benchmark to evaluate our claim that complex type data will perform faster than flattened data. In this micro benchmark, we set up some tables with user IDs and search words that would have been searched by each user. In our data set, we have 1 million users, each of whom has searched for up to 1,000 distinct terms. We set up our micro benchmark in a 4-node Vertica cluster segmented on the username column. Here's our 3 tables. First, we have our flattened traditional table, where we have a username column and a word column for the search term. For each username, we'll have 1 row per search term, so we can expect to see many rows with the same username. Next, we have 2 complex type tables. First, we have the words array table, which pairs a username with an array of distinct search terms. In this table, we can expect to see 1 column or 1 row per user. We have a similar table next, which is the words set table. This is the same as the words array table, except instead of using an array complex type, we have a set complex type, which organizes the data in a sorted fashion for fast lookups and keeps only distinct search terms. We ran 2 queries over this setup. The first query, in English, is trying to count the number of search words used by each user. For the flattened words table, this is a pretty straightforward SQL query with 1 group by clause. Select username, count words, group by username. In our complex type tables, instead of using this group by clause, we just use a different function, the apply count function, which iterates over an array or set and counts the number of non-null elements in it. The second query we ran was doing a lookup. We want to find users that specified a specific search term. So with our flattened table, we can run select username from words flat, where words equals Xbox, for example. For the complex type tables, we just have to tweak this a little bit. Instead of words equals search term, we're going to use the contains function to check if our array or set value contains the particular search term instead. Here's some performance results. The first query did a lot better. We see a 5 times performance improvement when we use the array column, and we see that the set column ran this query 6 times faster. For our second query, finding users who had a specific search term, the array table performed twice as fast, and the set table performed almost 3 times as fast. In addition to having the queries run faster, we derive another benefit from using the complex type data as well. Both the array and set tables used 80% of the storage space that was needed for the flattened table. Next benchmark we ran was compare a normalized schema versus complex data types. We built another benchmark to evaluate the claim that the normalized schema would have slower performance and more memory usage than a comparable query on the complex type data. Our benchmark was based on the web sales schema that Deepak introduced earlier in this presentation. Our dataset consists of 100 million sessions, each of which contains up to 10 items ordered and up to 10 page counters. We stored the data in HDFS in the Parquet file format. In English, our benchmark query is trying to find the page with the maximum duration spent and the ship date of the customers who ordered more than 5 items in a session. Our normalized schema has these 3 tables: a web sales table, an orders table, and a page counters table. In contrast, the complex type data only needs one table, web sales, where we have a complex type to represent the orders and page counters columns. This was the query that Deepak showed earlier. It answers our benchmark question. As we see, it's pretty complicated. Let's contrast that with this query, which answers the same question against the complex type data. Instead of some joins and some group bys, we just have a pretty straightforward query with a predicate. Admittedly, one of our expressions has a couple nested functions in it, but nothing too scary looking there. When we ran these, the join query took 151 seconds, and the complex type version took 110 seconds. This speed up is just under 30%, so that's a pretty nice improvement. But what we really want to look at here is the improvement in memory usage. The query with the join, the normalized query, took 15.5 gigabytes to run. The complex type query took about half a megabyte. Do the math, that's a pretty gigantic improvement. All right, so we've established that complex types do perform to our expectations. So let's think about some best practices for using them. Well, first, when should you use them? You should use them when it makes sense, when you have queries that can exploit data locality, where you can help to avoid duplicating some data, or when your data is sparse. If you have any of these needs, then complex types are definitely going to help you simplify your queries quite a bit, as we've seen. When using complex data and complex arrays, use array bounds wherever possible. These are a good hint to the resource manager that will make queries use less memory and probably run faster. If you don't care about element order for lookups, if you want to ask the contains question a lot, then it's also a good idea to use set types. All right. Let's take a look at what you can do with complex types in Vertica 11.0. First, we have complete support for complex types in the Parquet and ORC file formats. You can create external tables over using copy statements on files of these types and then query any type of complex data. Next, we have a bunch of supported functions that you can use to analyze the complex data. The explode function will take an array and transform it into a series of rows with one row per array element. You can use the toJSON function to transform a complex value into a JSON string. We have a number of array functions as well, some of which we've seen in this presentation. We have contains, we have array find, array count elements, and there's some others as well. You can create views on top of your complex data. You can use field selections and array indexing in a create table as select statement. This is, of course, limited to types that are supported in ROS tables. The last full complex type feature is robust SDK support. You can write UDXs which read complex type arguments and produce complex type return values. We have a number of other features we're also still building, which can be used today for one-dimensional arrays. The JSON, Avro, and Kafka parsers can all be used to load one-dimensional array data. We also have the string-to-array function, which transforms a string into an array of the type of your choice. Bounded arrays should be used with one-dimensional and complex data. To parallel our explode function, we also have an implode function, which you can currently use to aggregate a column into a one-dimensional array. Next, you can cast between different arrays. You can transform your array of integers into an array of varchar, for example, and you can export one-dimensional arrays to Parquet files. We're also building JDBC client driver support. If you query a complex type column using the JDBC driver, then you can get your array and set columns back as java.sql.array objects. And you can get row and map types back as java.sql.struct. You can access all of these with the result set methods getArray and getObject. So we've already built a lot of stuff. Let's see what we're looking at adding in the future. Our top priority is to extend Vertica to allow complex type data to exist in ROS files. Once that's done, we're going to look at building out our JSON and Avro support to have those parsers emit strongly typed complex data. Next on our list is the unnest function, which is a function that is very similar to explode, just using a little bit fancier syntax. So it's a nice convenience function. After that, we'll build out some map support, so you can have strongly typed map data. Then we'll take a look into exporting complex types, whether to Parquet files, to org files, or to a delimited file format. We will someday combine Flex with strong complex types so that you can handle semi-structured data very efficiently. And we'll take a look at augmenting our database designer to give recommendations about whether or not you should use complex types. We're also going to take a look at our other client drivers and evaluate whether we should add native complex type support in them as well. Thanks everyone for attending and listening. Now I'll turn things back over to Paige for a question and answer session.
Thanks, Ryan. By the way, if you want to learn more after the conference is over, remember that our Vertica Academy is always available for free on-demand training and certification. Now we're ready for Q&A. Hi there, and we have a lot of good questions. Fortunately, we have a little bit of time to answer them. Okay, so I'm going to dive right in with the top voted question. Are complex types always better than using a join? Who wants to start? Deepak?
I can start, yes. Yeah, so complex types essentially add another dimension to the database design. So we saw that the joins incur not only extra performance cost, but also storage cost. And now when you look at joins, they're pretty much introduced by normalization. So if you look at the traditional reasons why we normalize, you basically have first the 1NF where you have a table within a row and then you want to normalize it. And that's where complex types do best. And the other normalization, the 2NF and 3NF, we try to avoid duplication data. And in that case, it's a trade-off between locality versus duplicating the data. So the short answer is in most cases, joins are very heavy in terms of memory, and complex types will definitely avoid that overhead. But again, it's a database design question. If you have a lot of locality that can be exploited and there's not much duplication of data, then complex types will definitely give you a good benefit.
Good to know. All right. So we'll throw the next one to Ryan. How do I write a query that discards elements of an array?
So we have, at the end of the talk, I mentioned the explode and the implode functions. So if you want to take an array and then discard some elements or transform them or what have you, then you can use a subquery with the explode function to turn the one array into a series of rows for each element. And then you can use the implode function to group them back together after applying your predicate or function or what have you.
Okay. All right. Back to Deepak. What are the size limits of a complex data type?
So we have internal value to control the size limits, but essentially, yeah, there is no limit in the theoretical sense. You can have any number of elements until the maximum row size. So that's what limits the number of elements in a complex data type.
All right. Let me see here. Okay, so Ryan, how do you store complex data types in a columnar storage format? I think that's what that's asking.
Gotcha. So at the end of the talk, we say that putting complex types into ROS files is sort of the top thing on our roadmap. So I guess the cheeky answer is we don't. We read them from Parquet files. But the better answer is the way we represent things now. You know, I mentioned that we have these structure columns and we have the values columns earlier in the talk, and that's more or less our plan, is to put complex data into ROS using that same representation that we have in memory. So it'll look roughly like one ROS file per field of the complex type.
Sounds good.
Just to add to
All right.
that, both Parquet and Arc are columnar, and they do represent complex data types in a columnar fashion. So ROS will also be able to do that.
So it's already being done, and we're working on doing it internally as well. All right.
Right.
Go ahead.
I was just going to add a little extra detail. So ORC and Parquet actually have pretty different ways of representing a complex data in both in a columnar fashion, but they look very different inside the file. And so the representation we're intending to adopt is going to be more similar to what the ORC format does.
Good to know. All right. So what about performance impact for insert, load, etc.?
So we don't have. I can take that. So yeah, we don't have full support for ROS yet, but since it's columnar, we will have those optimizations to copy and load as well. We are implementing complex types in a columnar fashion. So Ryan, let me know if I missed something, and I'll probably add to that.
Well, I think it's a bit of a vague question, actually. Like, so what are we comparing against?
That's good.
It might be a good one for you to talk to folks with a little more depth at the Dev Lounge, where they can kind of explain what they're really asking.
I agree with that.
All right. I think we already answered that one. Size limit. Did I ask about size limits of a complex data type? I don't think I already did that one. When they upvote them, they change order, and then I lose track of which ones. Let's see, we did that one. Columnar storage, performance impact, size limits. Oh, compression. How do complex types affect compression? Brian?
Ryan, go ahead.
So that's related to the question that was already asked about how do we plan to store these things in ROS files. And since we are pretty much going to be splitting up the complex types into each of the fields and then storing each field in a ROS file, then we can expect the compression should be pretty similar to what you would currently get if you just load that, like if you load imagine your array elements, if you load that as just another column, in a normalized schema. The compression should be pretty similar. We've run some limited experiments that more or less validate this idea. So the compression should still be pretty good. Where you save is in repetition of the other columns. So if those other columns would be repeated for every single element of your array, if you had a normalized schema, then those columns are no longer repeated once you've transformed into having an array instead.
Okay, that makes sense. Question about the explode and unnest array. The question is it running in parallel or single-threaded? Deepak?
Yeah, it's a UDX function under the hood, so it is going to be executed in parallel.
Parallel.
Yeah.
Depends on how you choose the partition clause in your query. User-defined transform functions require a partition clause, which kind of specifies how well, or which gives a hint to how well Vertica is going to be able to parallelize it. And so in the case of explode, the over clause or the partition clause doesn't really have any functional impact, but it still needs to be there. So you can probably just stick partition best in there, and then Vertica will decide to parallelize it as much as it possibly can.
Okay. Let it figure it out. All right. So, and we're getting more questions. Let's see. Can I mix VMAP data columns with strong complex types?
Ryan, go for it.
Sure. So it's on our roadmap to do that better. One thing that you can do right now, or I should say when Vertica 11 comes out, is have a combination of both in Parquet files. Deepak, correct me if I'm wrong, but in Parquet files, once 11 comes out, you will be able to load a strong complex type from some subset of the columns in the Parquet file, and then you'll be able to have a different set of the columns be loaded as a VMAP into a raw var binary column.
Wow. Okay. So, which one is complex data types, flattened tables? When should I use which one? Are they complementary? Do they make sense? Does that make sense,
Sure, yeah.
Deepak?
So flattened tables, okay, so is this like flattening of the data, or is it the Vertica flattened tables that they're referring to?
I think they're thinking about
Ryan,
flattened tables in Vertica,
Ryan, do you
but
know
yeah, I think
the
it's
answer for that? Yeah, go ahead, Ryan.
Well, I mean, they're kind of different approaches to a similar problem, which is trying to get rid of a join.
Yeah.
We haven't run that comparison yet, but that would be a good experiment to try. I think that's a good Dev Lounge question.
yeah. Sounds like one maybe you could even dive into right there. Let's see. How are the elements of an array type stored? Separate columns or single column? I think that's since they're in Parquet or Norc, that's more of a separate. Let's see. What's the trade-off between normalization and a complex data type?
Yeah, I think we saw the results already. So when you normalize, you'll incur the join overhead. And yeah, we saw that join incur both extra memory as well as they are slower against when you use complex data. We have the whole benchmark demonstrating that advantage of complex data types.
Okay. So using the complex, you save the join time. All right. What would the predicate be for the question? Give me all rows whose underscore. You know what? I'm going to have to, let me, it's a SQL thing, and saying it out loud would make no sense. Let me paste it into the chat. There we go. So it's like, do you use contains or what to give me all rows whose array value contains the value 42 at least once?
Yes, so contains will give you if that array contains the element. And yes, so if it's at least once, so it will give you the answer for this particular question. So apply contains is the right function.
Okay. That's the so yes is the answer to that one. Yes, you would use contains. All right. I think the only one left is how elements of array type are stored. No, we did that one. When will Vertica support arrow format?
That's another question for the Dev Lounge.
Dev Lounge. All right. Yeah.
There are
Pretty much
many
any of
components to that. So.
yeah.
Yeah.
Any question that requires some back and forth with the developers, where you need to kind of ask them questions and they got to ask you back questions and get some more details and maybe even dive into the application and actually look and compare. That is the perfect thing to go to the Dev Lounge and talk to folks about. As far as the questions, I don't see any new ones coming in. So unless you guys have some new questions coming in, I'm going to go ahead and wrap it up. And thank you. You guys have been great for sending in all of these questions. It's a really good list and wonderful participation. Now, don't forget to go to the Analyze to Win section on the event navigation panel and then choose this session and enter the code for this session, which is PUG. And by doing that, you will gain some points and possibly win some prizes, but you will also help donate money to Jill Deshay's Out of the Cage, and that's a great cause. So stay tuned. Thank you again for being a great audience, and here's a word from our platinum sponsor, Pure Storage.
Pure Storage FlashBlade, the leading unified fast file and object platform, or UFFO, is built to address the needs of modern, unstructured data and consolidate workloads on a single platform. FlashBlade delivers performance, simplicity, and scalability to power the most demanding workloads while enabling modern analytics and delivering unmatched data protection, rapid restore, and ransomware protection, all with less downtime thanks to non-disruptive upgrades.